So in today's video, we are going to do contour maps, and we're going to dive deep into multivariable functions. So contour maps are special because they're not necessarily in 3D, they're more in 2D. So as you can see, all these graphs or the axes that I've drawn, it only has to do with y and x values, but contour maps are basically maps out the various possible functions out of a multivariable function. So in our first example, for example, we have f of x comma y, and this notation basically is the multivariable version rather than what we've previously learned with regular functions. So rather than f of x having like the variable x only, so like x plus 1 for example, we now have both the variable x and y. And the key to drawing contour maps in today's video is by setting f of x comma y equal to c. So in today's video, it's more about like a visual representation rather than computing like the derivatives and finding the limits and all that. For now, it's just we're looking at it visually. So for our first example, we have f of x comma y equals to x plus y. What we want to do is we want to set this equal to a constant, so we can call it c. So if c is equal to x plus y, we want to basically isolate y. So to isolate y, obviously we want y to be by itself. That's pretty simple. We get negative x plus c. And the reason why we're isolating y is because if you think about graphing any function, we usually want the y to be by itself. And so now this becomes something that's familiar, but we don't know what c is. So as we defined earlier, c is anything. It could be a constant. It's just anything. So we can set up different numbers, but by the end of today's video, your goal is to be able to identify how to graph contour maps without necessarily computing or like graphing all the details of the value c. But we will do this first in the beginning just to really understand what's happening. So if we have y equals to negative x plus c, we can set c equals to negative 1. We can set, I don't know why I used colons, but c equals to negative 1. We could do like c equals to 0, c equals to 1, c equals to 2. So if we do that, we plug in c, and we have these different versions that I've written. So here, c can be negative 1, it could be 0, it could be 1, it could be 2. And we see that we have all these different functions. And what we're going to do for contour maps is to graph them. So let's say if I just graph these 4 functions, I have y equals to negative x minus 1. It's just a linear function with the y-axis at negative 1 with a slope of negative 1. So it's just going to like go downhill. So let's just do something like this. Is this a slope of 1? Let's just do this. It's not the most accurate, but let's just say this is, yeah. So there's that y-axis at negative 1, and then we have just y equals to negative x. So one thing to note with contour maps is that it's functions after functions, so it doesn't necessarily have to be, you know how like when we have something like this would not be considered a function because it doesn't pass the horizontal line test, but a contour map is like a map, right? It maps out the different versions of different graphs combined together, and so it's okay in this case to have overlaps. So we have y equals to negative x plus 1, so that means, you know, a y-axis of 1, and then y equals to negative x plus 2. So notice how the slopes are all the same, and this is kind of what a contour map is. And yeah, I mean, there you have it. If you want more c values, there's more different versions. If I set c as negative 2, that means there's a y-axis at negative 2. So really, c could be anything, and I hope you guys see the pattern. We can clearly see that the slope remains the same throughout, and we're just changing c. So this is kind of what is expected when drawing a contour map. So now let's try going on to the second problem. Again, we set this as equal to c, and we want to isolate y, and we get y equals to c times x. So I guess by now you can probably imagine what that would look like. If we have different versions of c, that means we have different slopes of c. So it could be c equals to 1. Then that would be y equals to x. If c equals to 0, then that would be nothing. So let's not do that. If c equals to 2, we have y equals to 2x. If we have c equals to -1, we have y equals to -x. So there's both positive and negative slopes, but we notice the pattern here is that there's different slopes. So if we plug in, or if we graph y equals to x, then we would just have that. If we have y equals to 2x, that means that the slope is 2 and it's now steeper. If we have y equals to -x, then that's negative, that's going in the negative direction. So you can kind of imagine more different versions. If we have y equals to -2x, that's also possible if we set c equals to -2. That would just mean we have a steeper slope. And you can kind of imagine what that would look like as we draw more and more lines. So there you have it. And now moving on to the third problem. Again, set c equals to x squared minus y. We have y equals to x squared minus c. And again, we have different variations of c. So if I have c equals to -1, c equals to 0, or c equals to 2, then we would get y equals to x squared minus 1, y equals to x squared, y equals to x squared plus 2. So again, this is kind of similar back to our first problem because we have a quadratic function, but we can notice that we have different y-axes. So we have the parent function, which is just y equals to x squared, but we also have y equals to x squared minus 1, so that just basically shifts that down. I don't think I'm doing a very good job of drawing that, but you can kind of imagine what that would look like as we draw more and more and more of these. So yeah, it would basically, just different y-axis, but also x squared. So yeah, there you have it. This is kind of what it looks like for contour maps. I hope this helps. I'm sure practicing will definitely help, so I recommend you to do that. Otherwise, thank you for watching, and I'll see you guys in another video. Bye!